Welcome back to differential equations. Today we are talking about section 4.1 and 4.2. Let us open up with a theorem. Suppose we have a naught of x, a 1 of x, all the way out to a n of x, and a g of x, which are all continuous on some interval I, with a n of x not equal to 0 for all x in that interval. If x equals x naught in some for some value in that interval, then a solution y of x of the differential equation exists and is unique. And that differential equation is ANX times DNY dxn plus AN minus 1 x dn minus 1 y over dx n minus 1 plus all the way out to a0 x y is equal to g of x, given initial conditions y of x naught is equal to y naught, all the way out to y of n minus 1, the n minus 1 derivative of y at x naught is equal to yn minus 1. So this is what's called an existence and uniqueness theorem. This is one of the things both mathematicians and philosophers struggle with, which is existence and uniqueness. This gives us criteria. If certain criteria are met, then a solution exists, and more than that, the solution is unique. Let's look at an example. If I have the second derivative of y minus 4y is equal to 12x, with the initial conditions that y of 0 is equal to 4 and y prime of 0 is equal to 1, well, the a2 of x here is 1. A1 of x here is equal to 0. A0 of x here is equal to -4. And g of x here is equal to 12x. And we have y of 0 is equal to 4 and y prime of 0 is equal to 1. So we have that ANX is not equal to 0 for all x in an interval. And we have initial conditions required, so there exists a unique solution, y of x. That doesn't mean we can find it. In this case, we can, but the existence of a solution doesn't necessarily mean that that solution is easy to find. So let's look at a spot where this helps us out. Say I have the third derivative of y plus 4 times the second derivative of y minus y prime plus 7y equals 0. And we're given the initial conditions that y of 1 is equal to 0, y prime of 1 is equal to 0, and y double prime of 1 is equal to 0. A sub n here is 1, a sub n minus 1 is 4, and so on. G of x is not equal to 0, or g of x is equal to 0, but we don't care that g of x is equal to 0. We only care that a sub n itself is not 0. And we have initial conditions for y, y prime, and y double prime here. Since this is a third order differential equation, we have 3 initial conditions. So there exists a unique solution, y of x. Now, say someone else came along and said, if you just let y equals 0, you've met all of these conditions. The output is 0. The derivative of 0 is 0. So the output at 1 of the derivative is 0. The second derivative is 0. And if you plug in 0 to each point here, well, that is a solution to this differential equation. But we just said there exists a unique solution, only one solution to this differential equation. So this is the only solution. Because given these initial conditions, we were able to find a solution, and that solution was guaranteed to be unique. Thus, this is the unique solution to this differential equation. Let's compare this with x squared y double prime minus 2xy prime plus 2y equals 6, subject to the initial conditions y of 0 is equal to 3 and y prime of 0 is equal to 1. A sub n here is x squared, which is equal to 0 at x equals 0. And our initial conditions are at x equals 0. So we are not guaranteed the existence and uniqueness of a solution to this differential equation. We might be able to find a solution that exists for some interval, but we're not guaranteed that one exists. All right, I will see you in a few minutes for the next video.